how to get where you're going?
Yeah, all that, and I can't start my slideshow. Yeah,
Let's see.
thank you.
You're welcome.
Let's see here. Used to have a Mac back in the day. Let's see here. Yeah, I'm going to go right there. And there we go. Hello, folks. Good to be with you. How many got lunch? Good. I don't know if this is the siesta slot or the hangry slot I'm in here today. But Meg, thank you for that and for your remarks. Something I left out of my bio is I'm genetically predisposed to transportation issues. My dad, my uncle, my granddad all retired from GDOT. And my dad told me he started out cutting line on a survey crew when they were building I-75 in North Georgia. And he said for the first year, they wouldn't let him touch the instrument. He had to observe it. And then they let him carry it to the truck eventually after another year. But he became the assistant district engineer over construction out of Cartersville. And he used to tell me, Brian, there's three things you need to know about a road. It's got to be pleasing to the eye, soothing to the rear, and it's got to drain water. So we're here to talk about the third one today, right? Okay, here goes. And as usual, started out with too many slides. Now, I'm more of a baseball guy, but I'm going to start with Wayne Gretzky. Gretzky said, I don't skate to where the puck is now. I skate to where it's going to be in the future. That's why he's the great one. So today I'm going to try to emphasize this idea of how do we pragmatically skate to try to anticipate where the puck is going to be in the future, talk a little bit about accelerating human effects and climate change, land use change, et cetera. And I'm going to talk a lot about uncertainty, and I'm going to talk a little bit about complexity and how to deal with that. And so the theme of this talk is really thinking about infrastructure, not just as things out there in space, but as processes in time, but not making things more complicated than they have to be. So I was preparing for this event, and thank you very much for this opportunity. It's really an honor to speak to this distinguished group. There's a lot of old friends in the room, and such a wealth of experience and knowledge. So it's humbling to be here. But I was looking through some things, thinking about what I wanted to say, and I was looking at HEC 17 again, and ran across this thing, innovation through embracing uncertainty, and we've got Humphreys and Kilgore and Perez and others on that. And this is something I've said over the years, we need to embrace uncertainty. It's kind of abstract, but it's kind of uncomfortable also. And I'm probably already getting in trouble right off the bat here. But I'm just asking you, you don't have to give it a big squeeze. We just want to kind of give it a little bit of a hug today and see how it feels. The other thing is I'm going to quote Oliver Wendell Holmes. Now, I like figs. He says, I would not give a fig for the simplicity on this side of complexity, but I'd give my life for the simplicity on the other side of complexity. Okay? So we're talking about uncertainty and complexity. One thing we can say without uncertainty, with high confidence, that he had a great mustache there. Right? We'll try to figure out what that means. And then, I know I'm going to say some things and you're going to say, well, engineering standards and methods are already quite conservative, and maybe we don't need to do all this stuff you're talking about. And it is true. This is the code of Hammurabi in, like almost 4,000 years ago. said, if a builder builds a house for a man and does not make its construction firm, and the house he's built collapses and causes the death of the owner of the house, that builder shall be put to death. And if it causes the death of the son of the owner, they shall put to death the son of that builder. So engineering standards have been inherently conservative for a long time, and I recognize that. The other thing I'm going to talk about a little bit is how we talk about floods. I got all worked up during Hurricane Harvey, and they were talking, turn on the news, they're like, 1,000-year, 10,000-year flood or whatever. And I just got all agitated, and I wrote this thing and sent it. My friend Marshall Shepard said, you ought to send that to the Washington Post. And I was like, you're kidding me. You got to be kidding me. And I did, and they published it. It blew my mind, and it was really scary because then all these other people wanted to talk to me about it. But anyway, here's my outline. I'm going to talk about, the need for new lighthouses to help us navigate. We don't want to throw away our old lighthouses, but the need for new lighthouses. Some of the tools that Meg touched on, it's really important to keep advancing the practice and bringing the best tools and technologies to bear. And embracing uncertainty. I want to talk a little bit about nature-based solutions, natural infrastructure, and offer a few final thoughts. So the ASCE put out the 5-year roadmap to sustainable infrastructure. And that's where this lighthouse idea came from. They said now that the familiar lighthouses of the past may no longer be relevant, they're still relevant for the most part, but we have to have protocols, processes, and standards to navigate the unfamiliar waters of the future. And their whole thing is do the right project and do the project right? Shovel-worthy and do it right. And so some of the things we're talking about at this conference is how do you do it right? How do you recognize a good project? Now, there's a little tension here because on the other hand, I agree with Christina Swallow that a lot, I'm not saying folks in this room are doing this, but a lot of folks have become maybe a little too beholden to recipes and cookbooks and doing things the way they've always done it. And, judgment is what engineering is all about. That's why, for those of you who suffered through engineering school, it was to cultivate that judgment, not just follow a recipe and be a technician. So there's a tension there. We want the standards. We want to know how to deal with these future challenges, but it can't be too prescriptive. If we wait around for that, we'll be waiting a long time. Now, I got to have a few obligatory slides about stuff that's happening with climate and concerns. So this is hot off the press from my colleague Marshall Shepard, meteorologist at the University of Georgia. And what it makes no sense what you see there, but basically what it is a trend analysis. JAS is July, August, September. What it's showing is statistically significant positive trends in rainfall intensity here in the southeast U.S. And so as Marshall will say, the events are just getting juicier and there's more precipitable water in these events. And so we're seeing statistically significant increases. The literature is replete with evidence that, floods are being amplified. Here's Anna Barros' study in ASCE and so on. So, I think maybe this is old news, but this interaction of land use and climate, real things are happening, and we can't assume that things are going to behave in the future in the same envelope of variability that they've operated in the past. So we're in a changing operating environment, and everybody's talking about stationarity and non-stationarity. And all these papers in the literature, have you all read these? Stationarity is dead. This idea that we can look to the past to predict the future, that would be stationarity. And then all these papers, is stationarity dying? Stationarity is dead. Collateral damage from the death of stationarity. Stationarity wanted dead or alive. Stationarity is immortal. And then make stationarity great again? That's Gerard Hogan and McManus, right? And then we live in the Piedmont megalopolis, right? And it's this Charlanta, this monster keeps growing and all this impervious area. And how are these things how are they going to interact? The system level changes in land use and land cover and these juicier convective events and so on. You know, and folks have tried to crack into this, like AECOM and Michael Baker did this study, and, you know, they used some flood regression equations and plugged in different precip and impervious, and they basically concluded that our 100-year floodplains are going to increase, you know, by at least 50% or so. And then one other twist in this I'll throw out there, since we're all hydraulics geeks for the most part, you know, the channels are changing too, and that's where I've cast my lot for a lot of my careers, looking at, you know, channel instability and mayhem. And this study out of Geophysical Research Letters, Louise Slater showed that, you know, a lot of the increases in flood stages we're seeing are actually due to aggradation and channel change. Part of it's hysteresis in our rating curves and all that, but just think about it. Okay, we got land use, imperviousness, precip, channels changing all at the same time, stormwater systems not being maintained appropriately in a lot of cases, you know, tidal flooding, compound flooding, interactions between tidal, all that. Wow. So I'm going to show you, I didn't want this to be, hey, here's a sales job for Bledsoe's research or whatever, but I'm going to show you some research, not because I think it's so awesome. I'm going to show it to you with warts and all, but the things I'm going to show you are more like striving to find this balance between complexity and simplicity, but working towards a toolbox for resilient transportation infrastructure and you know, flood management. So thinking about just these three interactions right here, climate change, land use change, changing river channels. So we've been, a lot of folks have done this over the years. We've been working on this idea of probabilistic flood mapping. There's been a few papers recently by my PhD student, now graduated, Tim Stevens, if you want to check this out. But the idea is basically we do a stochastic Monte Carlo simulation, run HEC-RAS, you know, thousands of times. See, I knew it was the siesta slot. Some folks are letting their food settle. They're relaxing. That's good. The three things we're varying are discharge under climate non-stationarity, flow resistance, and channel change. And we basically run HEC-RAS about 1,000 or 10 to 10,000 times, drawing from each of those things. And you know, practically, a lot of folks are never going to do this, but I have something I want to propose. So let me show you an example here from McMullen Creek in Charlotte. McMullen Creek has shown really increasing flood risk levels. Flood frequency is non-stationarity there, highly significant positive trend. And so we run this kind of simulation on McMullen Creek, and what we see is that a lot of people have built right up to the edge of the flood insurance rate map 100-year floodplain. And when we do, we vary discharge and channel geometry and Manning's in a little bit, we see that a lot of people are living in the floodplain that didn't know they were in the floodplain or what level of risk that they had. And then we go in and look at some road crossings in here in the McMullen Creek watershed. And so what I'm going to do here, there's several road crossings here, collector, minor arterial, principal arterial. And so we go in and look at the distribution of water surface elevations at each of those road crossings. And I'm going to zoom in here on station 47083, one of those principal arterial crossings. And that box and whisker plot shows the distribution of water surface elevations that we get when we vary those three things within a reasonable range. And so there's the cross-section of that road crossing. And first we do it where climate is stationary. And we just treat it like it's a constant thing over time. And the road elevation is the red line there. Okay, and so in the stationary case, we overtop it often less with just, less than about 10%. And things are not so bad at this station. But then when we bring in the non-stationary case, we have, basically the 10-year looks marginal, the 25, 50, and 100. This thing is at high risk. And so when we look at the cross-section, the probability of overtopping is quite high when we do that analysis. And just to keep moving here, you can look at it, in a variety of ways. You can, if you like log Pearson 3 or run NHEC HMS or generalized extreme value, or, you have certain Manning's N values, you can do those things. But this bottom paper here is just out, and basically we came up, Tim mostly came up with a simplified approach for doing this kind of Monte Carlo analysis where you don't have to do the thousands of realizations, and it basically gives us a very similar answer. Now, maybe this is too complex, but it is striving to find practical tools that we can use to look at, to realistically depict the risk at these road crossings. Now, one other thing to keep in mind here in the southeast, the flash flood issue. Now, there's an interesting paper by Ashley and Ashley. It's a little outdated now, but what they found, they asked the question, who's getting killed in flash floods and what are they doing when they get killed? And the answer is over 60% of them are in vehicles, and the highest rates are in the southeast, males in vehicles at night. So, this is a serious thing. Now, here's what I think is a wonderful example of where these things could be brought together. This was a study that I think it was Andrea Hendrickson commissioned at Minnesota. I don't know if Andrea's here today, but I think this is an excellent study, one of the FHWA pilot studies where they took a region of Minnesota and they looked at the hydraulic capacity of the structures across that entire region. And an analysis like this simplified, streamlined, uncertainty analysis at structures across a region would be a really powerful thing to understand, to develop a transparent idea or description of what the risks really are. So a few messages from that part of the sermon. Often the uncertainty bounds at a hydraulic structure, the uncertainty bounds on a water surface elevation, even if we don't make extreme assumptions about these distributions, are often a lot more than a couple of feet or some typical safety factor when you really dig into this range of conditions that could occur at that structure. And what we saw when we ran these Monte Carlo simulations is that the greatest source of uncertainty in upstream water surface elevations was what's happening at the hydraulic structures. So in other words, the road crossings, when we map floodplains this way to tell people, the risk at their houses, the hydraulic structures are probably the most influential factor in determining that uncertainty upstream for the most part. And there are fairly straightforward ways of doing this kind of analysis, and this could be incorporated into making decisions about structured replacements and other resource allocation decisions. My understanding is a lot of states make their decisions about what structures they're going to replace or upgrade based on, purely structural considerations and not maybe so much hydraulic capacity. So this could be a step towards resilience. Okay, talking about floods, you all are familiar with all this, but I think it's important that when we communicate with our clients and the public and politicians, that we try to move away from the 1%, the 100-year, the 1% annual, the exceedance, et cetera, and maybe start talking about reliability over a planning horizon. So, if you do the basic math without any changing climate or anything, if you want to have 90% reliability meaning the probability that the bad thing won't happen, like the flood overtopping, if you want to have 90% confidence over a 30-year planning horizon, you've got to set the height to the 285-year event. For 90% reliability over 50 years, it would be the 474-year event. So you start talking to people like, well, you've only got, 50% reliability over the next 30 years of your mortgage. How do you feel about that? And they're like, I don't know if I feel very good about that. As opposed to saying, oh, it's a 1% annual chance exceedance. They're like, whatever. The research clearly shows that most people don't understand, the 100-year return period. And these numbers here are, again, stationary assumption. No changing anything. The past is like the future. The future is like the past, excuse me. Now, one last idea here, reliability also has a distribution at the edge of the floodplain. And so this is a really interesting thing to talk to people about, confidence in the reliability at the edge of the floodplain. But this is a paper that's about to be wrapped up in Water Resources Research, where Tim Stevens kind of figured out the math of how to do a non-stationary reliability analysis to get the distribution of reliability. So we talk with stakeholders about the kind of maps that make sense to them, working with social scientists, show them cartoons. Which one of these makes the most sense to you? It's clear people like maps that have gradations of uncertainty and contours, as opposed to this bright line in the sand that says you're either in or you're out of the floodplain, that binary kind of floodplain. And so, again, you can map this out as reliability. It shows that a lot of folks who thought they were staying out of the regulatory floodplain really are at quite high risk. And you can change the descriptions to things like knee deep, ankle deep, fast enough to sweep away a car. That's a power of 2D modeling, is that you can actually start putting intuitive descriptions on these different levels of flood risk. Okay, and one last sort of side tangent here. Some of the research we're doing on flood risk inequities, like in Athens-Clarke County, what do I mean by that? Some demographic groups are more exposed to flooding than others and are at higher risk. We find in Athens that the flood insurance rate maps miss a lot of these flood risks. And when we go in and use the census data and days of metric analysis, and we ask, what's the demography in these census tracts and blocks and such that have different degrees of flood risk, what we find are that Black, Hispanic, and low-income populations have, typically 45 to 185% higher likelihood of being exposed to flooding compared to the average demographic in that census polygon. And so why do I bring this up? Well, I think transportation infrastructure and decisions we make about our hydraulic infrastructure at road crossings could be part of the puzzle in addressing some of these flood risk inequities. Now, I really want to applaud some of the things that FHWA and others are doing with the 2D modeling. I think that's great. I think Brian Varela did this. He was one of my students out in Colorado, showing how CDOT is saving money using 2D modeling in terms of savings on riprap sizing and channel stabilization structures, bank protection structures, and so on. And I'm not going to really go into that because there's going to be a lot of discussion of that at this conference. But I think that's great. I'll show you one quick example where we used a little bit of 2D modeling. We started out with a question from GDOT, and we appreciate their collaboration with this. You know, what are the hydraulic effects of building temporary construction platforms out into the river? These so-called jetties that we use in building bridges. And so we basically ran HEC-RAS. You know, once again, this time we ran it 50,000 times. We created channel geometry that followed, scaling properties of natural channels and all these different width to depth ratios and slopes and so on. And then we tried a whole slew of different predictor variables. And the question was, can we come up with a simple, parsimonious model that tells us what the effect of these temporary construction jetties are on channel velocity and shear stress? And so we looked at all these different variables. I'll spare you the details, but the bottom line was we were able to identify an area ratio that was an excellent predictor of the changes in velocity and shear stress. This is a one-dimensional world, but using 1D allowed us to examine a whole host of situations. And so we were able to come up with some simple relationships for GDOT to take to the regulatory agencies and say, yeah, this is a reasonable estimate of, how much velocity is changing as a result of these different protrusions of the jetty into the channel. And then pull the 2D modeling out and ask, how far do these effects go downstream? And where's the maximum attack on the bank as a result of this? And then we can create a spreadsheet that they can use to show the permitting folks what the likely changes are going to be and how far downstream that extends, and then compare those changes in velocity and shear to the bank materials. How erodible are the banks? So to look at the erosive forces versus the resisting forces. Okay, enough of that. So a few musings on HEC 17. I think it's great. Now, looking at the different tiers or levels of analysis, you get to tier 5, and these would be highly consequential situations, right, where the consequences are pretty grave. And basically, HEC 17 says, there's a lot of emphasis on the flows of water and getting additional insights into what's happening with climate and future climate and so on. I'm going to argue here for an additional set of analyses that might be worth considering. It says, in level 5, you might want to do some customized modeling to evaluate resilience of a project. And in the section on reducing vulnerability, it says think about debris, stream geomorphology, channel stability, sediment transport, what's going on, with the channel. So I believe that ought to be part of almost every analysis of a structure. And so we did this little project called NCHRP 2440, and the idea was design hydrology at bridge crossings. And again, I'm not trying to sell you on this research. I'm trying to show you an example of where we strive to take something that's really complex and uncertain and come up with something that's fairly, excuse me, practical, trying to hit that sweet spot between simplicity and complexity. So the idea is basically, can we look at relative sediment transport capacity, at a structure, what's going on upstream with respect to transport capacity relative to what's happening at the structure. So this is an old analytical channel design approach. And so why do we care about this? Well, a structure that has some semblance of sediment continuity, and we could throw debris in with that, is a safe structure. It's going to have, obviously, you guys know this better than I, less maintenance issues. We're trying to reduce the risk of aggradation, degradation. So it's just going to be a better structure, save money, be safer, and also have more ecological benefits, most likely. So when we did the implementation training for this, we had lots of examples of where sediment was out of balance at structures, whether it was Southern California or Kentucky or other places. But the idea is pretty simple. Now, a lot of folks say, sediment transport, it's a bunch of voodoo. Well, and there's such huge uncertainty and errors. But my friends, when you look at sediment transport capacity in a relative sense, here's the capacity here versus down here, those relative differences in capacity and the potential to move or not move sediment can be quite accurate since we're not predicting it in an absolute sense. So we're essentially integrating sediment transport capacity over time to look at aggradation, degradation potential along the channel. And so we created this spreadsheet tool, and some folks have used it. I'm going to go through these slides really quick, but Casey Kramer and the folks out at WashDOT used it on a project out there, this culvert replacement, and they were interested in the salmonids and the aquatic organism passage. And so this is coming down off of Mount Baker, I think it is. And so long story short, they needed to come up with some semblance of an equilibrium slope for this channel in the culvert replacement, and they're trying all these different slopes. And so they used this so-called capacity supply ratio tool. It's an Excel spreadsheet to evaluate these slopes. Now, it is possible you could take a 2D model and pass results back and forth if you wanted to get the hydraulics dialed in a lot better. This is very simplified with respect to the hydraulics. But suffice it to say, this tool helped them come up with a regional flow duration curve at an ungauged site, and that's used to look at the cumulative sediment transport over time. And then you got this spreadsheet where it'll help you integrate that transport in a supply reach and a design reach, etc. There's a few hoops you've got to jump through, a few steps, and then you get a range of analytical solutions. You get a range of widths and slopes that are estimated to provide sediment continuity. And so they picked one that they liked, and they built this thing, and as far as I know, it's going okay. Now, it's warts and all. This tool, has a lot of simplifications, but this is an example of trying to get to that other side of complexity. Okay, one other thing we did in that project was we asked, not all streams are created equal, so how can we evaluate stream response potential of different kinds of streams? And we really honed in on lateral and vertical adjustability based on bank and bed materials, distance to a hard point, flashiness, and energy level, like, specific stream power, watts per meter squared of flow energy. And we tried to say, okay, do all streams need to have the same level of analysis for sediment continuity? No. Or for channel change? No, of course not. And this is not a new idea, right? But trying to hit that sweet spot on the other side of complexity, we looked at all these different variables and ways of, simplifying this and tried to ask, okay, what are the characteristics that warrant a deeper analysis, a deeper dive into the design? And we came up with kind of a ranking of low, medium, high, very high response potential of streams, and then made some recommendations about the different levels of sediment balance analysis that could go with that. Okay, and part of that is getting out into the field. This is me walking around in Southern California. Upstream, I go down, downstream a little bit further, and I see the middle picture, and then I go downstream a little bit further, and I see a nice tension crack there on the bank, right? So this, working out in Southern California and other places where the channels are so dynamic, helped us think about all these different rapid geomorphic assessments, whether it's Andrew Simons and Peter Downs, or Peggy Johnson and Richard Hay, or Caltrans. And what we tried to do is take the best elements of these, incorporate some channel evolution model thinking. Now let me ask you this, folks. If there was a head cut moving up towards your structure, wouldn't you want to know that? If there was a channel upstream that was about to shift from channel evolution stage 2 to 3, where all of a sudden the mass wasting of the banks starts, would you want to know that? Because once you cross the geotechnical threshold for channel instability, all of a sudden you got a big sediment supply, and often you got a big wood supply. You would want to know that, wouldn't you? If your channel upstream is about to cross that geomorphic threshold from stage 2 to stage 3. So we incorporated some of those ideas here. Out in California, we didn't always see the channels follow this tried and true Shum, Harvey, Watson, Simon, whomever, channel evolution model. Sometimes the channels just went off into braiding land and kept widening. So anyway, we incorporated some of those ideas, bed mobility, distance to a hard point, and we started with all these variables, and then we said, wow, this is complicated. Let's try to simplify. Let's make a decision tree. Let's create some early off-ramps, come up with a parsimonious tool, and we kept whittling it down, and then we came to the primary factors that we felt like we just couldn't throw out because they were so primary. And so we came up with these little tables of ranking of channel response potential that we thought might be helpful for folks to recognize kind of high-risk situations versus not so high risk. All this goes back to the old trade-off diagram. How many have seen this before? Is this this basically, the idea is that modeling is a balancing act, right? On the one side, if the model is too simple, maybe it's fast, easy, cheap, but it leaves out some critical processes, fundamental things that really need to be in there, and it's so simple that it's not reliable. On the other end, things get so complex, they take so much time and money, there's so many inputs, there's so much uncertainty that it's hard to even understand the prediction accuracy that your model's putting out. So you're trying to find this sweet spot in the middle where the model is just as complicated as it needs to be to get the job done. What does that mean to get the job done? Well, it has information that is of a sufficient accuracy to at least inform a decision. There is a signal there that can inform decision making. So some messages: get out of the car, look around. Think about incorporating geomorphic assessments and sediment balance as part of your analysis of trying to respond to all of this change that we're seeing in these challenges where things seem to be moving outside the operating range of the past. So I tried to give you a couple more examples of pursuing that other side of complexity. You never get there all the way, but you try for it. And I think it's great that, we have these documents, and the new one on the right has some really good examples of bringing in geomorphic assessment and considerations of sediment transport and channel stability. So check that out if you haven't. Okay, so embracing uncertainty. Now, uncertainty is, where we don't have perfect knowledge or prediction power. And there's lots of different kinds of uncertainty, right? There's the kind we tend to think about our model uncertainty, but there's also the uncertainty in what the forcing or the inputs, the drivers are going to be in nature because they're kind of stochastic. And then there's decision uncertainty. And you read the literature, they say, well, yeah, the progressive view of uncertainty is not to ignore it, reduce it, eliminate it, or cope with it, but it's to embrace it, right? Just like they said in that other document. But this is scary because sometimes you just don't want to embrace something. And, if you go around talking about how uncertain you are, you're concerned. It's going to scare people. People think you don't know anything. This is Frank. He's a greeter at Walmart. Frank was a little too frank about uncertainty, and that's his retirement plan now. No offense to Frank. So reasons not to embrace uncertainty, right? Sometimes it's scary. We all have our excuses, right? Our models are good enough. We don't need to look at all these ranges of variables. We know what the inputs are. We know what the parameters are. Politicians are not going to understand it anyway, or they're never going to use it to make a decision. I can get any answer I want. It takes a lot of time. It's a pain in the neck, etc. If you read one paper, if you haven't read it, I would encourage you to read this paper by George Pappenberger and Keith Bevan. Ignorance is bliss, and they sort of systematically debunk each one of these arguments, I think, pretty well. The benefits of embracing uncertainty are, I think, better decisions, better stewardship of resources, and learning by doing. Why aren't the design folks and the maintenance folks talking more? Not just about individual projects, but about patterns and things that are happening so that we can close that feedback loop to, design better structures based on what we're seeing at the structures we've built in the past. So I really like this diagram from some Army Corps publications. Charlie Yo put this together. It's really a question of how deep is the uncertainty and how grave are the consequences of being wrong. And he sort of splits it into these 4 quadrants and says, if it's really grave and it's really uncertain, you should do the full-on uncertainty analysis. If it's pretty grave, but your uncertainty is, not that much, then sensitivity analysis is a good way to go. And HEC 17, has some good steps in this direction as far as saying, look at these different confidence intervals, depending on service life and that kind of thing. And this is a good step in the right direction. A really simple one from the sediment transport world is like, what's going to be the change in flow of water versus the flows and loads of sediment coming in? Worst case scenarios are they're going to be opposite of each other, right? We're going to have higher sediment transport capacity due to higher flow, but less supply, and therefore we're going to have degradation. Or the opposite, where we lose capacity and we have too much sediment and we get degradation. So you don't have to look at all the combinations. You can look at the combinations of most concern, those interactions like that. So just maybe a final thought on uncertainty here. I think it's important to try to communicate clearly about uncertainty, and there's a lot of tools you can use aside from Monte Carlo simulations and fancy graphs that a lot of people don't understand. And being careful, telling stories, describing scenarios, and being careful with our language. Things like, we're certain of the following. We estimate with confidence that this is the case, and so on. Being clear about those different levels of confidence. And being transparent about how our judgment is informed by that uncertainty and the analysis. Okay, last part here, just to wind it up. Everybody reads the ASCE report card, I know, and yep, and usually it's a D, right? C minus. There was something interesting that happened this time. The report card had a new way to raise the grade for resilience. It's down here at the bottom in the fine print. It says, enhancing the resilience of various infrastructure sectors by including or enhancing natural or green infrastructure. So that's the last thing I want to talk about real quick. Maybe you're hearing a lot about this. I'm going to propose that infrastructure is, the built environment that we're used to thinking about. It's also our institutions and operations and policies, but it's also our natural systems. All of those together constitute infrastructure. Now, the infrastructure bill or act defined natural infrastructure, and it basically is both natural systems and built systems, whether it's the dunes and the barrier islands that are speed bumps for hurricanes, or marshes that are dissipating wave energy, or floodplains that are relieving flood pressure. All of those things are infrastructure. And we have an ASCE committee focused on natural infrastructure. We've got a long definition, but suffice it to say, we define it very broadly to encompass both natural and created systems that use nature-based solutions, including stormwater green infrastructure, natural and nature-based features that the Army Corps likes to talk about that are specifically for flood risk reduction. It's all of these coastal and riverine features. And I think you're going to be hearing more about this, given some of the legislation and policies that are coming along that are telling us we've got to incorporate natural infrastructure and nature-based solutions into our projects. And my suggestion to you is that let's try to do that where we really integrate it in, and it's not just window dressing or a garnish. It's just a little side topping on the pizza after it's already been baked. Let's bake it in, try to bake it in from the beginning, whether it's thinking about how the reefs or the marshes or the mangroves or the dunes or these horizontal levees, these different lines of defense can work together with our conventional systems to provide more resilient infrastructure. So we got a great document from Brett Webb and others, Federal Highways document that talks about natural and nature-based features for coastal highway resilience. If you haven't checked that out, I'd recommend it. Green infrastructure continues to be an important part of our toolbox, stormwater green infrastructure. And the key point is it's not an either-or situation, right? Folks, we can blend the green and the gray into a unified system. Now, a lot of folks are kind of skeptical about this. They're like, we need engineering standards. We don't know how to do this. We'll never get it permitted. It takes too much space. It takes too long, those kinds of things. Those are valid concerns, but and actually sort of reinforced by a survey we did of ASCE, where the biggest things they cited as hurdles or barriers are the guidance and the standards and the empirical basis and the policy obstacles. But the good news is a lot of great stuff is happening where we're getting the engineering guidance, how to build these things, incorporate them into conventional infrastructure systems like the Army Corps' international guidelines that came out recently. This is the one that Brett did, and there's all kinds of resources available on how to design these systems and incorporate them into our projects. And it's not just touchy-feely stuff. There's a lot of great research going on to come up with rigorous engineering design standards. For example, we're working on how much wave attenuation can we get out of salt marshes in different conditions and different lengths of salt marsh so that we can incorporate that into design criteria. And, you know, it helps us quantify the benefits of those marshes and why we need to sustain them under sea level rise. And so coming up with scaling properties for the wave attenuation provided by the marshes, and also mangroves like the work Tori Tomachek's doing at the Naval Academy and out at Oregon State. So the idea is that the natural can work together with the conventional solutions, and that those green solutions, those natural solutions, are providing benefits 24 hours a day, 7 days a week. You don't see a concrete wall regenerating itself out of solar energy after it's been damaged by a storm. You don't see it adjusting itself to sea level rise like a reef, for example, or a living shoreline can. So think about the benefits flows over time by incorporating those natural features, and we get a lot more for water quality, habitat, and so on. So last thought is, you know, those can be combined into a system like they did at Tyndall Air Force Base. They're rebuilding that Air Force Base with you know, multiple lines of natural infrastructure features to protect the installation there on that barrier island. And so this has lots of applications in the transportation world. And the Corps and others are working on modeling toolboxes where you can actually plop down different kinds of natural infrastructure in a hydrodynamic model and evaluate its performance for, you know, a particular coastal setting. So a few thoughts here. You know, the natural infrastructure is a good complement to the conventional, and it helps us build resilience, like ASCE said in the report card. And sometimes it can do that at a lower cost in some situations, and it can be self-healing and adaptive to changing conditions. So I would encourage you to consider building that into your future designs. And here are my final thoughts. Finally, it ain't easy to embrace uncertainty and to get to that other side of complexity that Oliver Wendell Holmes was talking about. But I believe it's worth striving for. You never get there. It's a journey. But I think you folks are the ones that are going to make it happen. So I'm encouraging you to think of your infrastructure as not just a thing that's out there, but as a process in time. Let's try to be a little more transparent about these uncertainties, including accounting for, you know, changing conditions and non-stationarity, you know, the reliability over a planning horizon. And let's try to apply these tools like the 2D modeling and trying to look at sediment balance and channel instability as part of the process. Work towards that. And let's try to communicate a little better. You know, there's a lot to learn from what's happened. You know, they say it's important to learn from your mistakes, but it's even better to learn from other people's mistakes, right? So let's try to close this feedback loop where we see what's happening with these structures and we try to incorporate that knowledge and learning back into the design process through better communication, consider nature-based infrastructure. And I think hopefully I gave you a couple of ideas for immediate steps that could be taken. All right, that's it. Thanks so much. I really appreciate it. And sorry I may have gone too long, but thank you. So, no time for questions, right, Brad?
Well, we're going to have
Okay, Joe, the floor is yours. Thank you all. That last picture, by the way, were the many layers of old road beds in the Big Thompson Canyon out in Colorado. They're the archaeological layers there. All right.